The north pole of a magnet is moved toward a metal loop, as we can see here. What does the current in the loop do? Alright, so we have a few options. A clockwise current sets up a north pole or a south pole, or an anti-clockwise current sets up a north pole or a south pole. Now we know from Lenz's law that the induced magnetic field is going to oppose the motion of the magnet. So that means that when we get our magnet set up, we'll have a north pole at the front of the ring and a south pole behind it, because that will oppose the motion of this magnet. So that means that it'll be setting up a north pole in front of the ring. So what do we need to create that north pole? Well, we need a current. If we use the right-hand rule, and we know that the north has got to be on that side of the ring, then we can see that the current needs to be in an anti-clockwise direction rather than a clockwise direction. So our correct answer is C. An anti-clockwise current is set up, which will produce a magnetic field opposing the motion of the magnet. Question 11. Why is a motor more likely to burn out when it jams rather than when it is running normally? You'd expect that if something was running and it stopped, it would power down, right? Well, in fact, if you jam a motor, it'll burn out. So we have a few options for the reason for this happening. The large back EMF that appears when it jams produces an increase in current. Now, back EMF is in fact caused by a moving motor and not a stationary one, so it's not A. The motor coil has more resistance when it jams. That's not the case. If you just hold a motor or a fan or something in place, that counts as jamming it, and you haven't changed any of the properties of the metal. C says eddy currents in the coil when it jams cause the coil to overheat. When the coil is not moving, it stops producing any eddy currents that it might have been producing due to its motion. So it can't be C. Our last option is the effective voltage across the coil increases when it jams. Now, normally when a motor is running, it produces a back EMF that relates to part A. When it stops, the back EMF disappears. When the back EMF disappears, it means that there's nothing opposing the voltage through the motor. And that means that the voltage increases. If it increases, then the current increases, and we're able to burn out the motor. So that means that by preventing a motor from running, we can cause it to burn out. The reason for that is because there's no back EMF to prevent the voltage. Question 12. A motor is connected in series to an ammeter and a 12-volt DC supply. The resistance of the coil is 2 ohms. When the motor is operating at full speed, the ammeter reads 3.5 amperes. What's the best explanation for this? If we were to calculate our expected current from these pieces of information, the ammeter should read 6 ohms instead of just 3.5. So there must be something funny going on. We have a few options. The resistance of the coil is increasing. This will indeed reduce the current, but we don't have any reason to increase the resistance. Heat will increase the resistance by a tiny amount, but it won't produce a very noticeable effect, and certainly not the effect that we see here. The motor produces a back EMF of 5. That seems like a pretty good choice. We know that moving motors produce a back EMF. And if that back EMF opposes the initial voltage, then that will slow down the current inside it. Let's go through the other options just to make sure that neither of them are better than B. C, as the motor speeds up, frictional forces act against its motion. Now this seems pretty good as well, because we know that there is some friction between a motor and the carbon brushes. The thing is, the frictional forces won't really change the current through it at all. D, some energy is dissipated as heat energy and does not appear as electrical energy. While this is true, this is more to do with the relation of the heat generated in the windings increasing the resistance. So once again, although this does have an effect on the motor, it does not produce any noticeable effect, and certainly not one that will reduce the current by that amount. So our correct answer is B. the motor produces a back EMF of 5 volts. This back EMF will reduce the voltage from 12 volts down to 7. And if we look at the current produced by a 7 volt system with 2 ohms of resistance, we'll end up with a current of 3.5 amperes.